Morning. To welcome you to today's installment of the Royal Ontario Museum Cooperating Society Speaker Series. Today we have Dr. Rowan Martindale from the University of Texas at Austin presenting. Rowan is from Alberta. She grew up on a farm just south of Calgary. Did her bachelor's degree in 2007 in geological sciences at Queen's University in Kingston. In 2012, completed her PhD at the University of Southern California in Los Angeles, where for her dissertation she examined Upper Triassic reef ecosystems and their demise at the Triassic-Jurassic extinction. She then did a 2-year postdoc fellowship at Harvard, and in 2014 joined the Jackson School of Geosciences, University of Texas at Austin, where she's now an assistant professor. Her research involves both fieldwork and lab work, from large-scale mapping to thin-section analysis of microfossils. And research in her lab focuses primarily on determining how environmental conditions influence the evolution and extinction of marine invertebrate communities in the geological past. And today, Dr. Martindale will talk about ongoing collaborative research she's doing right here in Alberta, looking at a very exciting new Jurassic marine deposit close to Banff National Park. Rowan?
So when they first asked me for my title, I thought I'd go big and grandiose to be exciting. But really what I'm going to talk about today is this new Jurassic fossil bonanza that we've been working on. And this is called the Ya Ha Tinda Lagerstätte. So I'd like to first point out that none of this research would be possible without my collaborators. So I'm going to show a lot of data, including geochemistry, including vertebrate paleontology, invertebrate paleontology, biostratigraphy, and local geology as well. So this is really the summary of the work that a lot of us have been doing together. So I always like to start my talks with a slide about what motivates my research. So I think it's important that you're not just here for the pretty pictures of fossils, but so you also know why I do what I do. So the thing that really motivates my research is a concern for marine ecosystems today. And so to understand how marine ecosystems might deal with pollution or environmental change, I go to ancient analogues and see how those marine communities have survived catastrophic mass extinctions and more minor mass extinctions as well. So these ancient ecosystems are really going to help us understand what might happen to modern ecosystems today. So as I mentioned, I'm going to be talking mostly about the work that I've been doing on a site here in Alberta, and I don't think I need to tell anyone in this audience that Alberta has a tremendous wealth of exceptional fossils. And so what do I mean by exceptional fossils? Well, most people are familiar with the beautiful dinosaurs that we have in Alberta, the articulated specimens like this Black Beauty T-Rex, as well as the recently displayed nodosaur, ancient marine reptiles like this mosasaurus here, but there's also some exceptional deposits of invertebrates as well. And so the corite mines have also yielded some very beautiful ammonite fossils. So exceptional deposits are very important, not only because they preserve beautiful fossils, and everybody loves beautiful fossils, but they also help us understand something about the organisms themselves and the community that they're living in. So not only do we have articulated skeletons, so the whole skeleton of the organism together, we might also have soft tissue preservation, so skin, feathers, soft parts, gut material. And if we've got organisms that have no skeleton or shell whatsoever, like these Burgess Shale examples, this Anomalocaris here, we could actually be seeing whole communities that wouldn't be preserved otherwise. So these exceptional fossil deposits, which are together termed Lagerstätten, are extremely important and offer this rare glimpse at the history of life in a unique way that we wouldn't get without these exceptional deposits. These do also require some relatively exceptional environmental circumstances to preserve. So, for example, if we're going back to the Jurassic, where I work about 183 million years ago, we've got this beautiful Ichthyosaur from the Posidonia Shale Lagerstätte in Germany, and you can see that without the soft tissue preservation of the skin, without this dorsal fluke and the tail fluke, we would have a very different idea of what this animal would look like. So these deposits are very important. So what I'm going to talk about today is our discovery of this brand new Lagerstätte out at Ya Ha Tinda. And so the first half of my talk is mostly going to focus on how we found this deposit, what's in this deposit, lots of pretty pictures, don't worry. And then the second part of my talk will get into what these exceptional fossils can tell us about marine communities in the Jurassic, about the environment in the Jurassic, and how these organisms survived or didn't survive an extinction event. So let's start back in 2013, 5 years ago. I think probably most people, if you were living in Alberta at the time, even if you were living in North America at the time, were very aware of the 2013 floods. So this caused catastrophic damage and flooding, particularly along riverbeds. They ripped up new channels of river systems, and it was really a disastrous time for property damage and things like that. But they had this other knock-on effect, was that all this flooding, all this floodwater, ripped up a bunch of new material and exposed lots of new fossil sites. So this is something that the Tyrrell has been pursuing over the past 5 years, is trying to understand and collect as much of these exceptional deposits before they get eroded away. And so based on this little post in 2013, there was 140 new fossil sites, and this is not even including the one that I'm going to talk about today. So where was I in 2013? I was just starting my postdoc. I was very enthusiastic, trying to figure out what I was going to do for the rest of my career, trying to get hired. And a group of us started looking at this oceanic anoxic event in the early Jurassic, about 183 million years ago. And what we noticed is that there's been a tremendous amount of work done in Europe, but relatively little done in South America or off the coast of North America. So I joined a team from Virginia Tech, consisting of Dr. Benjamin Gill, who's an assistant professor there, and his grad student, Theodore Them, or Teddy Them, and we went to look at some sites in North America. So we took sort of a quick 2-week perusal, went to several different localities, and tried to see what we could find. So the chief goal of our field experience was to go out and try and find samples for Teddy's PhD thesis. He was looking at the geochemistry of this particular oceanic anoxic event. So we were looking for these black shales and calcareous siltstones. And when we were out on the outcrop, all of a sudden, Ben looks at Teddy and says, "Get off, get off." And Teddy says, "What? What's going on?" Ben said, "You're standing on a lobster." So lobsters are extremely rare in the rock record. They're actually not as rare as people expect, but if you go out to a marine site, you're not just going to find a ton of lobsters. And so we collected this lobster. We started looking for some of the other specimens that were in this riverbed. We started pulling up things like this little fish here. So this is the spine and the ribs. That's the skull with the eyeball and the mouth. And then some other things that had soft tissue preserved that we weren't really sure what they were. And so this sort of started this big research project trying to understand what's going on at this site. And so again, not only are we trying to document this brand new fossil Lagerstätte, we're also trying to understand what it can tell us about this particular event. So huzzah, we've got an exceptional fossil deposit. That's not only exciting to me as a paleontologist and paleoecologist, but there's some other things that are really exciting about this deposit as well. So this is actually the first marine Lagerstätten from the Jurassic of North America. So before the discovery of this site, what we had were 2 Lagerstätten in Europe. And so we had a relatively good idea of what communities look like in Europe in this sort of northwestern part of the Tethys Ocean. But we really had no idea what was going on in terms of soft-tissued organisms from the eastern Panthalassa, or northeastern Panthalassa. So this is really exciting. Not only do we have this new site, which everybody loves, but we can also start making comparisons between ocean basins. So what's actually in this deposit? What organisms do we have? I'm going to start with the big stuff, because that's what everybody likes. We've got fish and ichthyosaurs that have been discovered It's sort of hard to find some of the really big stuff because we've just been looking in a couple of creek beds. We haven't been excavating wholesale because this is actually on Parks Canada land, so we have to be very careful about how we collect. But this is a beautiful Sorhynchus fish, so this would have looked something like a swordfish skull, and that's been studied by Aaron Maxwell in collaboration with Andy Newman right here at the Trail Museum. We've also got some of these little teleost fish that I showed earlier. Again, there's the spine and the rib cage. This is the skull, so the eye socket there, and the mouth here. And what is also really exciting, and I didn't notice this when I was first looking at the fish. Again, I'm an invertebrate person. I showed it to Andy Newman, and he said, look at that. Those are the gills. So we're preserving these really fine structures even in the vertebrate specimens. We don't have any beautiful little ichthyosaurs like the one that I showed with the skin outline, but we do have a couple of large ichthyosaur specimens, some of which are still sitting in the back rooms just waiting to be prepared. So I don't have too much information about ichthyosaurs right now, but hopefully in a couple of years we'll have some more data on that. We've also got several echinoderms, mostly crinoids. So crinoids are still around today. They are sort of colloquially called sea lilies. This is an organism that's related to starfish, brittle stars, and sea urchins, and it lives on a little stalk that's made of little like poker chips all stacked up together. And so from the deposit, we have this beautiful calyx, which is that sort of flower-like top preserved. We've also got some of these long stalks, as well as some disarticulated material as well. And so something I'll point out is that we weren't the first one to discover this. I wish I'd discovered that. This was actually collected in the 80s. So there was a biostratigrapher that was out working these sites, and he would collect, named Russell Hall, and he would collect these exceptional fossils every now and then. So there's, I think, a handful of specimens that were collected. They were mostly collected in float. And so a couple of them got published on, but there wasn't really enough to say, here we have this exceptional fossil deposit. But I've looked at his notes, and I think he knew. So we were hoping to include him on the paper that we published about the new Lagerstätte, but unfortunately he passed away before we could do that. So this is certainly not all just recently discovered. There are a couple older discoveries as well. So we also have some crustaceans. This site is really exceptionally preserved several different types of crustaceans. So we've got one or two little shrimps. So there are the claws. It's a little bit of a zoom in there. Now black on gray rather than white on gray. Those are the little claws like that. And then a tail here. Not much of the body is preserved with this guy, but you know, these little shrimp fall apart pretty easily if they've been eaten or if they've molted their exoskeleton. We have a lot of lobsters, which is very exciting. So these are called Uncinid lobsters. The closest relatives that we have today is this little Hawaiian red reef lobster. So you can see he's got claws that look very, or at least somewhat similar to the claws of these Uncinid lobsters. And so here in this specimen, we have the tail back here. That would be like the tail like there. This is the rostrum, or the face of the Uncinid lobster, like that. And then up here we have two claws that are sort of overlapping each other, so they're a little bit hard to distinguish. And this is stuff that we've just started working on. I've got an undergraduate working on this material as well, so I've got lots of pretty pictures, but I haven't really resolved the taxonomy of some of these things yet. So one of the cool things about this site is that there had been a couple lobster claws collected previously, and some researchers, both Russell Hall and some researchers in Germany, had noted that these were different species. So based on looking at the claws, they said, oh, this is a different species altogether. And so if we look at the claws of that last specimen, it's a little bit hard to see here. I know, I apologize, but if you trace out the outline of the claws, you can see that it's the same shape as the species that had been described. So now, for the first time ever, we can actually see the entire specimen of this lobster. So this is going to be a really important lobster, because it'll actually tell us what the rest of the organism looks like, not just the claws. In addition to that Uncinid, we also have two other species of Uncinid lobsters. So while that doesn't sound necessarily particularly exciting, this makes this locality, the Ya Ha Tinda Lagerstätte, one of the most diverse places for uncinid lobsters at this time in the Jurassic. So again, when we've finally worked through all the taxonomy of this material, this will definitely be a really important deposit for these types of lobsters. We also have another type of lobster called an Eryonid, and so it's a little bit hard to see. Again, black on black can be somewhat difficult. So I've got a nice sketch of a similar lobster that was published in 1913. So let's orientate him so that it looks like the same as my slab. This little guy is on his back, so you can see his claw coming up like this. And then the rostrum and sort of face would be up here. And then these are the legs coming out, and the tail gets lost in the crack. So this is another new species. In fact, this is probably a new genus entirely. If we look at the notches on the edge of the lobster carapace, that's sort of how people distinguish one species from another. So again, this guy is going to need a little bit of work in describing this new species. The other really exceptional thing about the Ya Ha Tinda Lagerstätte is the preservation of coleoids. And so coleoids are cephalopods, so organisms like squid, vampire squid, and octopus. And so this beautiful piece that I showed earlier, which doesn't really look like much unless you know what you're looking for, this is actually the back end of something that would be related to a vampire squid. And so what we're looking at here, this sort of shimmery part over top, that's actually the muscle tissue that would have been on top of the organism here. Underneath, you can sort of see a little bit of this sort of lineation down here. That's the internal skeleton. It's not a skeleton like a hard skeleton like we have. It's kind of soft and chitinous like your nail. We don't have the tentacles or the eye, unfortunately, but what we do have is this big blob right here. And that's the ink sac. So this is pretty exciting. And I had a master's student, Selva Marroquin, who just finished last year, or I guess it would be 2016 now, and is doing a PhD now at Virginia Tech. And so most of the work on the vampiropods was done it was done for her master's thesis in collaboration with Dirk Fuchs. So it's not only that one specimen that we have, it's definitely the prettiest specimen, but we have lots of these gladii, this chitinous internal skeleton preserved. They don't look like much, but you can see the ink sacs very clearly in multiple specimens. So again, we're working on what this might tell us about how these particular organisms are preserved and what that might tell us about how these organisms lived. We have ammonites galore, which is really good because ammonites help us tell time, which I'll get into in a second. And this was actually what Russell Hall was originally working on when he was going out to these sites at Ya Ha Tinda. And this is now being studied by Andrew Carruthers. And so Andrew is our ammonite guy, so all the ammonite work in biostratigraphy is definitely thanks to him. We also have a ton of bivalves. So this is sort of where I came in with my colleague Martin Aberhan from Berlin, and we started actually looking at not only what bivalves we had, but how they changed shape, whether they got smaller or bigger, and what that can tell us about environmental conditions. So we have some clams, sort of similar to a modern clam that you'd see. We've got some large oysters as well as some little guys, and I'll talk more about that in the second part of the talk. And we have a whole host of other things. So we've got organisms that burrowed in the sediment, we've got tree branches and logs, brachiopods, and a couple of true squids, so belemnites, things like that. So this is really a rich deposit. So great, we have a new Lagerstätte. That's fantastic. But it's not just the exceptional fossils. Those are really cool, and there's a lot that we can do with that. But as a scientist, I'm also curious about what those fossils can tell us about the environmental conditions. What can we hope to learn about the Jurassic Ocean? And how can this site help us understand how organisms survived or didn't survive this anoxic event, particularly since this is one of the only really good deposits outside of Europe? So, to come back to it, in 2013, we were out in search of this Jurassic oceanic anoxic event. Again, this is about 183 million years ago. And so I'll give you a bit of a background about the oceanic anoxic event. I won't get into it too much just for the sake of time, but I should hopefully give you a little bit of an introduction about what's going on in this interval. So There are two stages that I'll be mentioning. So this is the early Jurassic, not the entirety of the early Jurassic, but part of the early Jurassic, the Pliensbachian, and the Toarcian. So at the end of the Pliensbachian and at the beginning of the Toarcian, there's elevated extinction levels. So that means organisms are going extinct. We also see a drop in the number of species in Europe. And we can look at this more statistically rigorously, and we see that many different kinds of organisms are going extinct. We see this all over the world, although there are, of course, local nuances as well to be aware of. We also frequently see a size decrease with taxa. So the shells that are made are getting smaller, things like that. So the other thing to point out is that this is not just one extinction. We actually see multiple different events. So for example, this is in ammonites. And specifically, I'm going to talk about the event that happens at the boundary between the Pliensbachian and Toarcian stage and the boundary that occurs at the oceanic anoxic event. So a little bit more about the oceanic anoxic event. This extinction horizon, or this extinction interval, I should say, correlates, it's occurring at the same time as a large igneous province eruption. So it's a large igneous province. Imagine a huge volcanic province, multiple volcanoes spewing out lava, but instead of just being one volcano, it's the size of this orange blob down here. So this is a massive, massive volcanic province spewing out a wide variety of carbon dioxide, sulfur dioxide, and other noxious gases, and this is really going to change how the planet works. So one of the other things that we can see is that we've got black shales deposited around the world. So these black shales sort of help us clue in to where we are in time. And we've also see this big perturbation to the geochemical cycles. So if the world is sort of just spinning normally, if nothing is changing and everything's going along in what we call a steady state, if we look at the carbon isotopes, they should be relatively flat because nothing's changing. What goes in comes out, and it's relatively stable. When we perturb the system, so if we throw a ton of volcanic carbon dioxide into the atmosphere, or if we bury a ton of organic matter, or if we heat everything up and suddenly melt a ton of terrestrial permafrost releasing methane, what happens is that kicks the system. And so we see this big spike, either negative or positive, depending on the forcing. But essentially, if you see a spike like this, you know something's pushed the system out of whack. So it's not just the large igneous province. Obviously, when you push the system out of whack, there's going to be a whole bunch of knock-on effects. And so we don't just see carbon dioxide rising in the atmosphere. We also see warming, anoxia in the ocean, which I'll explain in a second. We can get acidification of the ocean as well. This all influences the terrestrial system, so we start to see rivers eroding more and more sediment as carbon dioxide rises. And so all of these Earth processes are responding to this kick. They're responding to this change in the system. So I'm just going to say that we do have evidence for most of these things happening at the Toarcian oceanic anoxic event. Personally, the acidification evidence is a little bit less clear than some of the others. And if anyone has questions about this, I'm happy to go through the data. But again, just given time, I don't want to spend too much time on this. So what does this look like in a simple cartoon? Because we can talk about flowcharts and everything, but it can be very difficult to visualize. I should say that this is made for the end Permian mass extinction, and I have shamelessly stolen it from my postdoc, William Foster, who's actually now working as a postdoc with Dr. Martin Aberhan, who's collaborating with me on this project. But the large picture is relatively similar. So we have a large igneous province, in this case Siberian traps, but for the Toarcian event, we're looking at the Karoo-Ferrar large igneous province. That puts a lot of carbon dioxide into the atmosphere. This can lead to warming, which stresses the organisms because it's getting too hot. This can also lead to acidification, so as that CO2 dissolves into the ocean, it becomes harder and harder to build a skeleton. And you can also see warming at the poles. Again, you can see enhanced erosion as well. And all of that together comes in to expand what we call the oxygen minimum zone. So things that should be in oxygenated water start to lose the oxygen in the water column. So today, we actually have this oxygen minimum zone in our ocean. This is just a zone in the ocean where the amount of dissolved oxygen is relatively low. So here outlined in purple. And so if you've got a normal system, nothing's perturbing it, this oxygen minimum zone stays about at the same place. It might expand or contract a little bit, but it's not too bad. However, if we induce or if we put a lot of nutrients into the ocean, organisms can start using up all that oxygen. And so what happens is we get, instead of just an area that's relatively low oxygen, we can actually get a wider area where we've got expanded low oxygen conditions and even anoxic conditions, so even so little oxygen that organisms can't survive. And so if you're an organism that's living on the shelf here, if that oxygen minimum zone gets thick enough or rises shallow enough in the water column, that can be really bad for you. And so that's sort of the theory about what kills off some of these organisms in this oceanic anoxic event. So, how is this event recorded at Ya Ha Tinda? We've got a lot of data from Europe, which I'll talk about at the end of the talk, but how is Alberta the same, or how is Alberta different? And of course, because we're looking at a Lagerstätte, we can also start to answer different questions. So, for example, those vampiropods, they don't usually preserve because they're mostly soft tissue. So how do they respond to this event? So this is where this interdisciplinary science really comes together and shines, because if we want to understand how a community responds to a big perturbation to the environment, we need to measure the perturbation to the environment. We need to see how the fishes and the Ichthyosaurs respond to that change. We need to see how the bivalves and brachiopods respond. And so again, we want our geochemists coming in and providing some information. We want the vertebrate paleontologists and the invertebrate paleontologists come in and providing information. And when it all comes together, we can actually finally see the full picture rather than just a few puzzle pieces. So here's our deposit. I'm going to talk mainly about this one site. We've definitely done work at other sites in the Ya Ha Tinda area, but this is just the easiest one to show. So what I've got here on the left is a stratigraphic column. So this represents the different rocks that we see in the outcrop. So for those that are familiar with geology, these are mostly calcareous siltstones or calcareous mudstones, and they go up into true shales. So that's just recorded in this strat column here, with oldest stuff at the bottom and youngest stuff at the top. And then this is when Andrew Carruthers comes in, and he looks at the ammonites that we collect. And so ammonites go extinct really quickly, and they evolve really quickly. So often you'll find that ammonites only live within one particular interval of time, which is great, because if you find that ammonite in that piece of rock, you know that you're in that interval of time. And so Andrew came along, looked at all the ammonites we'd collected and collected some of his own, and sort of put together this series of ammonite associations so that we can put some timelines on where we are in the system. So these ammonites tell us that this boundary is right here, so between the Pliensbachian and Toarcian, and then some of these substage boundaries as well. So that's the biostratigraphy part of it. Then along comes Teddy Them and Ben Gill at Virginia Tech, and they can give us a little bit more information looking at the chemostratigraphy. So what we have here is total organic carbon. So there's really high amounts of carbon throughout this whole section, which is very interesting. That tells us that this is probably oxygen stressed for much of the time that we've recorded. And Teddy's created this beautiful carbon isotope curve, which very clearly shows this huge kick at the Toarcian oceanic anoxic event. So I can't always show this on every single slide, so what I'm going to do is in blue, I'm going to highlight the boundary between the Pliensbachian and Toarcian stage, and then in red, I'm going to highlight where the carbon isotope excursion starts. So essentially, above the red line is where we start to see the oceanic anoxic event really kick on. So here's the east tributary of the Bighorn Creek section. The Pliensbachian-Toarcian stage boundary is there in the blue line, and then in the red, we have the Toarcian oceanic anoxic event. So the next question, of course, is how does the fauna change across the Pliensbachian-Toarcian boundary and at the Toarcian oceanic anoxic event? And more so than that, we don't just want to know who dies. We want to know what happens to the survivors. So how does this faunal assemblage that makes it through, what do they look like? Are they clearly stressed, or are they doing okay? And so for this, we're going to look mostly just at the shelly organisms because we have enough that we can actually do statistics on those organisms. So we've got our lithostratigraphy here, we've got our chemostrat. Now we can start adding in the organisms that we see. So before I was just showing pictures out of context, but now we can start putting on those vampiromorpha, or sorry, the vampire squid. We can start indicating where in this section they're from. So again, here's that stage boundary. Here's that onset of the carbon isotope excursion that marks the oceanic anoxic event. And so we can start to look at what organisms go right through and what get taken out by the oceanic anoxic event. Like I said, to do the statistics properly, you need organisms that are really abundant. And so we're going to do this with bivalves and brachiopods. I'm going to show 2,200 data points, and so I'm going to walk you through the chart before I show you those data points. So here's our lithostratigraphy on the left-hand side. The first thing to note is that these colors indicate what that organism is. So whether it's a clam of one particular type, or an oyster, or a brachiopod. So what's alive? Obviously, we've got our lithostratigraphic chart, so oldest is the bottom, youngest is the top. Here's our stage boundary, and there's our carbon isotope excursion, marking the oceanic anoxic event. And then on the left side, we'll have number of individuals, so how many bivalves or brachiopods are preserved in a particular bed. And on the right, we'll have how big are those organisms. So these will be dots for each individual specimen that we measured. And then I always forget to point this out, so note that on the bottom there is a log scale. So a shift up here to the right is much more significant than a shift down at the lower part where we're just going from 1 to 2 rather than much bigger steps at the upper part of the graph. So if we look at the number of individuals, you can already start to see that the color of dots down here are a little bit different than the color of dots up here. I'll get to that in a second. We see a lot of individuals on bedding planes down here, so this is clearly times when organisms can proliferate, when there can be lots of different clams around. And up here, even though we're in this carbon isotope excursion, we still see quite a few organisms on bedding planes, so that's kind of interesting. If we look at the size, we can start to see some pretty big differences. And again, I'll step through this in a second. But the biggest thing is that the colors down here are different than the colors up here. So across this red line, across the onset of the carbon isotope excursion that marks the oceanic anoxic event, we have a very different group of animals. We can go beyond colored dots, we can be statistical about it, and we can do what's called a cluster analysis. And so this is just plugging all the data into a computer and saying what's similar to what. And the two biggest clustered groups come out as being those that are before the red line and those that are after the red line. So organisms that were alive before the oceanic anoxic event and organisms that lived through the oceanic anoxic event and after it. So in addition to different animals, we can look at the number of animals that are around. There's lots of animals at the bottom of this section. It decreases a bit up section up to that onset of the oceanic anoxic event. But we still have quite a few within the oceanic anoxic event, and I'll talk about that in a sec. But right at the top, we go down to very low numbers of animals. If we look at the sizes, this is where we can see a really big change. No pun intended, sorry. We go from very large organisms down here in the Pliensbachian and in the earliest part of the Toarcian. Once we hit that oceanic anoxic event, they become very small very quickly. And they stay small for the rest of the section. So let's walk through time because it's great to look at charts and graphs, but that's not really helpful, especially if you're not familiar with this kind of a system. So what I'm going to do is step through this section and sort of give you an overall view of the different time steps that we've identified. So down here in the bottom of the section, this is before the oceanic anoxic event. We've got a relatively low diversity of organisms, so we still don't have tons and tons of life. We have some different types of life doing pretty well, but they're quite prolific. So we've got big shell beds where we see lots of clams, lots of oysters. The oysters themselves are getting very large, which says to us that there's probably at least enough oxygen that these things can survive for many years at a time. So this is a relatively good time to be alive if you're in this region. We can also look at the size, and because not everyone's familiar with looking at histograms, I'm going to sort of walk you through, first of all, if you've got a symmetric histogram like this, either unimodal or bimodal, you've got a relatively even number of juveniles and adults. If we see a left-skewed histogram like this, you have very few juveniles and lots of adults. Right-skewed histogram means that you've got lots of juveniles and very few adults. So in this early interval, we have relatively even distributions. They're either unimodal or bimodal. The Gryphea are a little bit right-skewed, but I think that's just driven by a couple of very large specimens. And so what we can say about this community is that they're alive for long enough that you're seeing multiple generations. Also in this time interval, we've got a lot of our benthic community. So we've got those beautiful crinoids, as well as the lobsters living down here. As well, we've got quite a diversity of lobsters, so we've got at least 3 or 4 different species of lobsters that are living down here in this lower part of the section. Curiously, we only see burrows, so organisms burrowing the sediment, down here below the blue line. This is really the only big change that we see at this blue line, is the loss of burrows. However, there's also parts where there's no burrows down in this part of the section, so it might just be that we didn't find them, or that burrowing is a little bit more ephemeral than some of the other organisms. And if we look at the vampiropods, we actually have a really high diversity, relatively speaking, of these soft-tissued organisms down here before the oceanic anoxic event. And they're mostly just right here, right before the oceanic anoxic event. And so keep in mind that we're not just looking at a complete picture of what's preserved. Soft-tissued organisms, if there's lots of oxygen, if there's stuff burrowing up the environment, they might not get preserved. So what we might be seeing here is the difference of they're surviving but not getting preserved, whereas here they're surviving and getting preserved. So it's a little bit of nuance to it, which complicates things a little bit. Once we get into the oceanic anoxic event, we see complete turnover. So the bivalves and brachiopods that we had alive in our Ya Ha Tinda area all go extinct, and we see new organisms come in. So these are pseudomydeloides, like this guy here, as well as some oysters that live attached to ammonites. These are called Leostria. And so we see a wholesale turnover of the community. And whereas before we saw mostly organisms that lived on the bottom of the seafloor, these pseudomydeloides do live on the bottom of the seafloor, but some of them can hitch a ride. So they can hitch a ride to organisms up in the water column, like these ammonites. If we look at the size distribution, it's a little bit right-skewed, but it's not too bad. So these things are probably surviving to adulthood, and we're seeing multiple generations. When we get up into that negative part of the isotope excursion, so the phase 2 of the carbon isotope excursion, we see again a different community, largely dominated by Bocetra, bivalves, and these little Meliagranella here. So these organisms tend to do really well in low oxygen conditions. If you throw very low oxygen conditions at them, everything else dies, but these guys do okay. If we look at sizes, this is really where this stands out. These Meliagranella are all about a millimeter in size. They are teeny, teeny, tiny. And the Bocetra as well are quite small. And so when we plot up the size distributions, what we see are a lot of juveniles and very few adults. We actually even see some of the larval shells attached to some of these Meliagranella. And so what we think is happening here is that this oxygenation of the water column, the amount of oxygen in the water is fluctuating every year, every month. And so these things are getting a foothold, starting to survive, and then getting killed off. We go into stage 3, and we actually see Pretty similar stuff. So the Meliagranella becomes a little bit more important, but we still have the Bocitra and the Pseudomyloides. But what I want to point out here are these little nests of Meliagranella. And you can't see it quite well on this picture, but these usually cluster around fish bits. So fish skulls or fish vertebrae where there's lots of phosphate. So good hard substrate, lots of food. And so these little guys come in when there's just enough oxygen to survive. They go crazy, and then 2 weeks later or a month later, they're all dead. So very sad. When we get into this post-isotope excursion, this is where the isotopes start coming back to normal. This should be when the community starts to recover. We actually don't see that at all. We see continued low abundance. It actually starts to become very difficult to find an organism at all. So you'll rifle through a lot of rock and find one little brachipod or one little oyster, but really not a lot of organisms up in this upper part. And again, if we look at the size distribution, we see a lot of juveniles and not a lot of adults. So what we're seeing here is sustained stress. So things are staying really bad, even though by our isotopes, it looks like we should be recovering. Also, just to point out, above the onset of the carbon isotope excursion, we don't see any more complete lobsters. All we have are the claws, and they're mostly this Uncinid pacifica organism. And claws are kind of interesting. Claws can float, so they may be coming from somewhere else, or it might just be that this guy is really robust. Hard to say at this point. And then if we look at the vampiropods, we do have 2 or 3 lineages making it through, but they're not as diverse as they were before this event. So this is really important because we're not only capturing an extinction of the organisms that live on the bottom, but also the organisms that live up in the water column. So as a scientist, I want to not just focus on the anoxia. I want to actually query whether it's some of these other things that are killing off the community. And essentially, if we look at the extinction patterns, so what dies, what survives, as well as whether they're getting smaller or bigger, or whether they're becoming organisms that can be less energetic or more energetic, we can start to knock off a couple of these things. And so acidity, food shortage, and an inhospitable substrate really just don't match with what we're seeing at Ya Ha Tinda. And again, if you would like me to go over the exact details of how we've gotten here, I can, but for the sake of time, I won't. So really what we see is oxygen stress being the predominant thing that's killing off our animals. Although, it has to be said, none of this is operating in a vacuum, so thermal stress is probably a problem. There might also be a few other things that are causing this community to get hit when the oceanic anoxic event starts. So one thing that I like to highlight is people always think fossils are great. Fossils are good for lots of stuff. But fossils can also tell us about paleoenvironments, which is a surprise to probably none of the paleoecologists, but can be a surprise to other geologists or the public. And so we can look at the kinds of organisms that we have, how big they are, how they live, and we can figure out something about how the oxygen was interacting with the sediment and with the water column at this time. So in that pre-oceanic anoxic event interval, what we have is a little bit of oxygen stress. This is not a great time to be alive, but it's an okay time to be alive. We see huge oysters. We've got that nice distribution of sizes, so we've probably got multi-annual episodes of oxygenation. So the water is oxygenated for multiple years. Based on the geochemistry, it does look like we still have times where there's anoxia as well, so no oxygen in the water column. But again, this is really where that interdisciplinary science comes in and can really help us understand the whole system. If we look at the interval within the oceanic anoxic event and after it, we see something very different. So we see these organisms that can survive low oxygen doing quite well, but even those organisms are still mostly juveniles. And so what we have is probably short-lived pulses of oxygen in the water, on the order of weeks to months if we're looking at the Meliagranella, or if it's Pseudomyloides, it's probably a little bit longer. So what we're looking at here is not just water is oxic, water is anoxic, water has no oxygen in it, but we're looking at something a little bit more dynamic, which makes sense. The planet is quite dynamic. Even now, we're seeing the oxygen minimum zone, especially off the west coast. The oxygen minimum zone rises and falls throughout a particular season. And so what we're thinking is, again, we don't just have anoxic water columns. We have this oxygen minimum zone that's coming and going and fluctuating on an annual, subannual, or decadal scale. And that's what's actually killing off these animals. It's not just everything goes anoxic. So what about the rest of the world? Well, obviously there's a lot of data in Europe, and so the first thing we did was said, okay, well, how does our stuff compare? And if we're looking at the bivalves and brachiopods, it actually compares quite well. So those proliferations of Bocetra and Pseudomytiloides, the teeny tiny little clams, we see that in Yorkshire and we see that in Germany as well. So this seems to be a global phenomenon. There's also some differences. So obviously nothing's the same all over the globe. There's got to be some differences. So there are a few clams that are unique to Canada that we don't see in Europe. And also Ya Ha Tinda has lower diversity. So probably this system was stressed from the beginning. We can also look at the recovery patterns and the extinction patterns. And in Europe, we actually start to see the extinction starting much earlier than we see in Canada. But we also see the recovery of organisms happening much quicker than we do in Canada. So in Canada, this whole time period is bad for organisms. Organisms stay small, organisms stay stressed. If anything, we see fewer organisms at a time when in Europe, they're starting to recover. So this is starting to tell us something about the global ocean, not just one particular site. And bringing it back to this exceptional fossil deposit, this is really exciting for me because this is starting to tell us something about how fossils are preserved, not just what fossils are preserved. So at this oceanic anoxic event, we actually have 3 Lagerstätten. So that's amazing to me, 3 that are occurring at the exact same time in different places around the globe. So maybe these oceanic anoxic events have some kind of control of how fossils are preserved. Although there are some interesting differences, and I've got hoping to get a PhD student or a postdoc to work on exactly how these things are preserved. But let's just sort of take a quick look in pretty pictures. From our site at Ya Ha Tinda, we've got lots of fish. They have relatively similar fish over in Germany and in the UK. But interestingly, they also have a group of fish called the ganoid fishes. And I have never seen a ganoid scale at Ya Ha Tinda. These guys are everywhere in Germany. So there's something very different about the fish that are in this particular part of the Tethys versus over here up in Alberta. We also haven't found any beautiful large marine reptiles, much to the chagrin of some of the people here at the Terrell Museum. But keep in mind, especially when we're talking about Germany, this site has been quarried for 300 years. These sites are actually used for fuel. And so there's meters and meters and meters of rock uncovered every day. When we go out, we've got 3 weeks, and we've got jackhammers, and we've got our backs to carry the fossils out on. So we're looking at a very different collecting situation. We can also look at these vampiropods, and there's some similarities. So for example, we've still got these ink sacs. They actually look like similar organisms, so similar species, but the preservation is quite different. You'll see this white look, which is phosphatization in the German specimens, whereas ours are quite different. So again, this is something that's going to need to be studied by a student. Lobsters are pretty cool. Like I said, we've got lots of lobsters out in Ya Ha Tinda. It actually looks like we have the same genera, but different species. So same sort of ancestral lineage, but some unique species in the Alberta region versus the Tethys region. But you can see sort of overall shapes are similar: Eryonid, Uncinid, and then, I don't have my Uncinid, but the claw that's just a little bit different from the claws in Europe. And lastly, Seriocrinids we find in both places. So there's some really exciting similarities that I'm looking forward to digging into over the next couple of years. But again, there's still quite a bit of difference. So see this beautiful sort of golden glow on the on the specimens here from Germany, we don't have hardly any of that in Canada, which is great because the golden glow comes from pyrite, which destroys fossils. So it's better for us, although it's slightly less pretty. So one of the things that we're currently working on, that my incoming student will probably spend a lot of time on, is trying to understand how these specimens are preserved. And so what I'm showing here is element maps of the tip of the claws, so this top claw coming down to meet the bottom claw of one of these uncinid lobsters. And we can map what elements are where. So there's a lot of silica in this matrix. There's a little bit of sulfur in the claws, quite a bit of phosphate, and quite a bit of carbon. So this tells us that carbonization and phosphatization are both helping us preserve these fossils. But each different type of organism might preserve differently. If we're looking at the bottom of the section versus the top of the section, we might see differences in preservation. So this is going to be a really interesting question to dig into, because this might tell us something important about how we get these exceptional fossil deposits. And then once we've done that, we can do a compare and contrast with Germany and with the UK, because again, we've got these Lagerstätten that are occurring at the same time. So global controls should be the same, and now we can look at how local controls or controls based on what organism is getting preserved, how that might influence these types of preservations. So to just wrap up, I'm very excited to announce that we have a new Lagerstätte in Alberta. So this can add to the plethora of beautiful fossils that we have at Alberta, and I've been so happy to work with the Tyrrell Museum. It's been really fun to quite literally come home and add some science to the Alberta paleontological landscape. We also have a high-resolution record of what's going extinct across this particular interval, and this sheds some light on when and why things are going extinct in this particular event, this oceanic anoxic event. We do see some similarities to Europe, but of course there are local variations, and so this is why it's really important not just to look at one site, but to actually go globally and see how things are changing around the globe. We really only see one main extinction here in Alberta, which is quite interesting. We see complete bivalve and brachiopod turnover. We lose a lot of our benthos, so organisms that are living on the seafloor, the lobsters and crinoids. And we also see very little burrowing. And lastly, we see no evidence of recovery in this section at Ya Ha Tinda. Obviously, the rock continues up section, but for the part we measured, we should be getting recovery up here, and we're not. So that tells us that this part of the globe is actually quite stressful for organisms. And then lastly, this is something that I like to constantly remind my colleagues who are not paleontologists, is that fossils aren't just stamp collecting. We're not just collecting fossils for the sake of collecting pretty fossils. I mean, it's one of the things we do, but fossils can actually tell us about the environment, about an extinction event, and about survival. And so by collecting all this data, we're not just collecting these beautiful specimens for future study, we're also helping ourselves understand what went on at this oceanic anoxic event, and this can hopefully tell us something about how these organisms survived or didn't survive a particular perturbation to the system. So lastly, I would like to thank the Tyrrell Museum and Parks Canada. They've been very generous in allowing us to work at this site. And of course, as I've mentioned throughout the talk, this is an interdisciplinary effort. So not only the collaborators on publishing the papers, but the people who got us out to the site, who helped us schlep all these fossils back to the Tyrrell Museum, as well as the other experts at the Tyrrell and around the globe who've helped us figure out what kind of organisms we have. I also have to thank our funding sources. So we've got a lot of different funding for this work, both student grants as well as National Science Foundation's grants to both Dr. Ben Gill and myself. So we've been very lucky that we've been able to have the money to do the research that we've wanted to do.